Hello everyone, welcome back to your Power Hour live lecture series for NEET 2025, and this time we are going to start with a new topic, a fresh topic, EMI and AC, electromagnetic induction and alternating current. Alright, so let's continue. Electromagnetic induction. Alright, fine. So let's take this good example. We all know that in such kind of power plants, the hydroelectric power plants, we see the dams. The mechanical energy due to these, let's suppose the water stream falling down from a very high up or whatever the reservoir is, it gets converted to electrical energy. What concept they use in this is nothing but your electromagnetic induction. The motion of a coil that is utilized to convert it to the electricity. Check. Alright, fine. As per the previous trend, the previous data of your NEET exams, I can say that safely 2 to 3 questions are asked. Approximately 2 questions are asked every year in the NEET exam. Okay? So that way this chapter is quite important. Okay. So let's start with the first topic of EMI, the magnetic flux. What is magnetic flux? Through magnetic flux, you guys would get a quick idea as we have studied the electric flux. Flux basically means the flow. Magnetic flux means the flow of field lines. Now, if the field lines are there, the magnetic field lines are there, and they are passing through a particular surface, then I need to find the flux crossing that surface or the flow of field lines which is passing through that surface, and that quantity or that thing, flux, is basically the product of magnetic field, the value of magnetic field intensity, and the area through which the magnetic field lines are passing. So the magnetic flux is defined as the surface integral, and the symbol of magnetic flux we use generally is phi. So phi is integration of B dot ds, where this is the general formula. B is the magnetic field and this ds is a little area of the little portion on the surface. Check it. Now there are a few aspects about this magnetic flux we need to discuss. First of all, this integration accounts for the non-uniform magnetic field. So be it uniform, non-uniform, this formula is valid in all the scenarios. Magnetic field and area both are vectors, so we use the dot product. Check. And whenever the dot product comes, the maximum value of dot product is when both the vectors are parallel. So if you see that this is the area given to us and these are the magnetic field lines, area vector is always perpendicular to the surface of which we are finding the area. The normal to the surface is in this direction. Magnetic field lines are also in this direction, so I can safely say that they are parallel. If they are parallel, we are getting the magnetic flux to be maximum in this case, because the angle between the two will be 0 and the cos 0, you guys all know, is 1 maximum. Check. 0 flux when the angle between the normal vector, the area vector, and the magnetic field is 90, and then any general value when the angle is anything like theta. So why have we written just BA cos theta there, and why have we written this integration? So it is because of the uniform and non-uniform magnetic field. Let's discuss this thing. First of all, the most general scenario, non-uniform magnetic field. Non-uniform magnetic field. What is non-uniform magnetic field? Basically, whenever the magnetic field in this space, in this region, wherever we are studying it, is non-uniform with respect to different positions. So its value is changing. Let's suppose कि I have horizontal field. ठीक है? Horizontal field. And it is passing through a surface like this. This is the surface it's passing. But what do I see? The magnitude at the topmost point was some B1, and later on it was some B2, and then I saw it was some B3, and so on, and they all are different. It's continuously varying. So what I can say, that since at each and every point magnetic field intensity is not same, I need to find the flux using integration only. So it will be B at that particular point. I'll take the little area through that point, the patch, okay, patch area, little ds, and then I'll integrate over the surface. I get the net flux. That's it. Check. Whereas, suppose the field is uniform. So for uniform field, uniform mag field, we need not put any integration and it will be simply the dot product. So magnetic field is uniform everywhere, and you guys know ki if the area is given to us, then I can easily find. Area vector shall be perpendicular to the surface, and in this case it is parallel, can be anything. Okay. So the flux is simply B dot the area vector, no integration, and the dot product is BA cos theta, like this. Get the point? Okay. The general scenario, why this cos theta? As we saw in the last example, if the field lines are like this, and supposedly the surface through which I need to find the flux, let's suppose like this, is bit tilted, the area vector if I draw of this surface will be perpendicular to the surface, definitely not horizontal. In this case the magnetic field lines are horizontal, so I can see that it kind of makes an angle theta with it. It is given to us, the theta angle has to be given to us. Then the magnetic flux through this shaded area will be, the phi is the symbol of flux, and remember theta is something else, it's an angle. So it will be BA cos theta. Remember theta is the angle between the normal vector, the area vector, and magnetic field. Okay. So let's take a quick example and let's get the answer of magnetic flux. They are saying a circular disk is there whose radius is 0.2 meters. It's in the uniform magnetic field whose magnitude is 1 by pi. Now note the unit of magnetic field. I know ki unit of magnetic field we know or we use is Tesla, correct or not? But here they are using something else. Why? They are using the unit in terms of flux. So what is the SI unit of flux? SI unit of flux, by now you all should know this thing, is Weber. So you know ki flux is magnetic field into area, so that's why they have taken magnetic field as flux upon area, Weber per meter square. So I hope you guys understood the unit. To remember these things, they can always play with the units in such a way, continue forward, that its axis makes an angle theta degree with the B. Okay. So axis means the area vector is always along the axis of a circular disk, so it's the angle we need. Theta is 60 itself, and now we just need to put BA cos theta. That easy, straightforward. It's a circle, so the area will be pi r square. Cos 60 we know is 1 over 2. Let's cancel it, and 0.2 square, so 0.2 into 0.2, cos 60 is 1 by 2. So it is 0.02, and that is the flux. Units going to be Weber only. Meter square gets cancelled. A option. That easy. See, such kind of straightforward easy questions have come in your NEET exam, and it came in AIPMT 2008. So you guys getting the idea? Alright. Let's carry forward. Let's move on to the next part of EMI, the Faraday's law of electromagnetic induction. So you guys have an idea about the flux. You guys have an idea that the EMF can get induced, and now the Faraday's law gives us the idea about this. Okay? So what they say, the magnitude of induced EMF is equal to the rate of change of flux with respect to time in case of a loop. If we have a closed loop and the magnetic field is changing, or the flux is changing by changing the magnetic field, by changing the area, or by changing the angle. 3 ways. So we can get the induced EMF. Next case, In the case of a wire, and it's not a loop, it's just a section of a wire, and it is the rate at which the magnetic field lines of force or magnetic field lines are crossing that wire. Okay. So the induced EMF here is equals to minus of rate of change of flux d phi by dt. Minus sign just indicates that the EMF will be induced in such a way that it's going to oppose the cause which produced it, the change in flux, because the flux was changing. That's why the EMF was induced. So it's going to oppose the cause which produced it. Okay. They have mentioned the unit of magnetic flux as Weber. We guys already know this thing. Let's move on. Fine. So discussing about what are the three ways in which we can induce the EMF or induce the current. They are saying we have a coil and there is a magnet. We can move the coil forward and backward, or we can move the magnet forward and backward. According to this, there will be some induced current we can see. Why is that? If you know the magnetic field intensity near the poles of a magnet is very high, that means if I move it forward or backward, the magnetic field intensity of the lines which is crossing this loop is changing. As we move the magnet nearer, the magnetic field intensity will increase. Now see, I know that magnetic field lines are going into the plane or they are crossing towards the left side and it is increasing. So what the EMI or this induced current will do, it will induce in such a way that it is going to oppose the increase in the field. So it should induce in this sense so that the magnetic field due to induced current, I know a loop is there, so current carrying loop produces magnetic field, and we can use the right hand thumb rule to get the magnetic field. So it should produce in this sense to get the magnetic field opposite to this increasing field. Get it or not? And this is done by your Lenz's law. Okay, let's take an example. They are saying magnetic flux linked with a coil given by the equation. So phi here first of all is given as 5t square 3t plus 16. Okay, the magnitude of induced EMF at t is equals to 4. So if we are just finding the magnitude, let's just differentiate it. Minus sign, we know what it represents. So right now I am just bothered about magnitude. Differentiate this with respect to time. So differentiating this expression, 5t square plus 3t plus 16. Sorry. So 5t square becomes 10t, 3t becomes 3 and 16 becomes 0. This is the EMF induced. They are asking at t equals to 0, so I am going to put the value of t as 4. T equals to 4 seconds. Now at t equals to 4, it is 40 plus 3, 43 volts. Straightforward. Isn't it very easy? And it was asked in your NEET 2020 exams, the October attempt. Okay, so easy questions only, very easy. Let's move on to another problem. Good problem. Let's check this out. Coil is there and now there are 100 turns. So remember that whatever flux you are writing for one loop in the coil, coil has n loops, so the total flux through the coil is going to be n times this one flux, b times a. So it is NBA. Okay, I guess many of you would quickly guess what is NBA. Alright, not now. So number of turns are 800. Effective area is 0.05 meters square, kept perpendicular to the magnetic field. Okay. Why it is kept perpendicular? Because if it is kept perpendicular, then only the magnetic field lines will cross. And the area vector is perpendicular to the surface. So they both become parallel. So we get the maximum flux. Okay. Fine. So magnetic field is there. When the plane of the coil is rotated by 90 degrees around its coplanar axis, in 0.1 seconds the EMF induced, the average EMF this time. Okay? So I know कि EMF is d phi by dt, or average EMF will be just the change in flux upon time. Now see, if it is rotated 90 degrees, let's say like this, okay, this was the coil and magnetic field lines were perpendicular. I rotate it such that it becomes parallel to the magnetic field lines. Now tell me, magnetic field lines are like this, and instead of keeping the surface like this, you are keeping the surface parallel to magnetic field lines. This is the surface, and this is the direction of magnetic field lines. So I understand that the flux will now be 0. So initially we had some flux, and now the flux is 0. So I'll keep this change in flux, just the magnitude I need, okay? So the initial flux I'll keep as NBA, and the final flux was 0, so magnitude will be this, and the time we already know. So I hope by now many of you would have already got the answer. So it will be 800, magnetic field is 5 into 10 to the power minus 5, and the area is 0.05 meter square. The time taken is 0.1. Okay, so let's remove one decimal from here and one decimal from here, and one more decimal, and we'll make it 10 to the power minus 6. Okay, so here I'll write the EMF. It will be 8, and this is 5 and 5. So 8 into 25, and then it is 10 to the power minus 4, correct? Minus 6 and 2, that's minus 4. So this will be your 200 into 10 to the power minus 4. Denominator, we don't have anything else. So it is 2 into 10 to the power minus 2, which is 0.02 volts. Straightforward. We got this 0.02 in another problem also. That's how you solve the problems of EMI, electromagnetic induction. I hope it was quite easy. Next one. Okay, it's in the NEET 2016 exam. A uniform magnetic field is restricted within the region. Okay. Radius r, the magnetic field changes with time at the rate of dB by dt. The loop 1, this is the loop 1 of radius r greater than small r encloses the region r, and a loop 2 of radius r is just outside the region. Okay. Region of magnetic field as shown in the figure, then the EMF generated is, let's check the options, 0 in loop 1, 0 in loop 2, and this EMF, which is the rate of change of flux in 1, and this again the rate of change of flux. Okay. Now you need to understand how do we find the rate of the change of flux. So here what you are going to see, in this one the magnetic field is only in this region. The magnetic field is nowhere to be found in this region. So here if we don't have any flux, and they are not saying these magnetic field lines are going around and coming back to this. Nothing is happening like this. Only this loop is having the magnetic field. So this will have 0 flux. And if it is having 0 flux, then its flux is also not changing. So there won't be any EMF in this loop. E2 is going to be 0, straightforward. And for this, you need to understand that radius of your loop is capital R, this one here, but the flux is only associated with small r. So I need to use the flux through this small r region only. So if I write the flux, it will be B into pi small r square. And to find the EMF, I know it is minus d phi by dt, and dB by dt is given already. They are saying it's changing at dB by dt, so it is minus dB by dt into pi small r square. So in the loop 2, the flux is 0, and in the loop 1, the flux will be B times pi r square. So the EMF is minus B and minus dB by dt times pi r square. So option D. This is how you can easily guess this thing. Straightforward problem, nothing so fancy, nothing so difficult. Next thing, the Lenz's law. We discussed in the starting that in the EMI, you guys know how to judge the direction of induced EMF or the induced electric current. The thing is I said in a statement the induced EMF always tries to oppose the cause which produced it. Who produces the induced EMF? The changing magnetic flux, the changing magnetic field. So they are saying according to this law, EMF will be induced in such a way that it opposes the cause which has produced it. The The figure shows a magnet which is approaching this thing. Okay? We just saw this example. So I know that magnetic field lines are going towards the left side and they are increasing in magnitude because they are closer here. So the current should be induced in such a way, let's say it's going like this in the anti-clockwise sense in this loop, so that its induced magnetic field will be like this, and that's how it induces the EMF. So the induced EMF or the induced current will be anti-clockwise in this loop. This is through the Lenz's law. Okay. Next thing. In this chapter, we start from the magnetic flux and then we find the induced EMF through the rate of change of magnetic flux. Now the thing is motional EMF. Why the motional EMF? It's also the case of electromagnetic induction. It also gives us the induced EMF, but how? It uses a little bit different concept of your magnetic force on the charges. Motional EMF. Alright. So we'll just write the formula of motional EMF. It is BLV. Now, how do we get this BLV? Basically, if you remember, in the magnetic field, a charge is moving and it's moving in the external magnetic field. Does it experience a force QV cross B? In the yesterday's class we discussed, yes, it experiences a force QV cross B. Now let's suppose that we have a rod here. Okay. Charges are there, many charges are there in the metallic rod, and it is moving like this in the magnetic field. So it's going to experience the force V cross B will be upwards. So I say that the positive charge deposits at the top, the negative charge deposits at the bottom. Opposite way. Tick. Now what happened? The positive charge intensity increases and the negative charge accumulates. So they themselves produce an electric field. And due to that electric field, the remaining charges will stop moving. So what I can say, if the remaining charges stop moving and they produce the electric field downwards, so I can say that charge E into the electric field is balancing your charge E into V cross B. So the electric field is going downwards, correct or not? So if I can say electric field is going downwards and it is balancing this direction, so what's the direction of V cross B? If it was upwards, correct or not? It was upwards, and this will be the positive terminal. So through this BLV, I need to just use V cross B and the direction of the positive terminal of this EMF, or the higher potential side basically. Okay? Higher potential side will be along V cross B. Okay? Velocity is in this direction, magnetic field is into the plane, so this terminal of the wire will be at the higher potential and the magnitude of EMF will be BLV. Okay, like this. Let's move further. Okay. So the moving rod is equivalent to the following diagram electrically as a battery. Okay. So we just put the battery, it should have some internal resistance, wires can have internal resistance, and the induced EMF is BLV. Okay. Now they are saying that instead of a wire, if we have a loop, okay, kind of a loop, AB is one wire and ACB is another wire, so they both get the induced EMF. The net loop won't have any overall cyclic EMF, but the terminals A and B will have a potential difference. What did I say? Loop is there, EMF induces if the flux changes, d phi by dt. But here technically the flux is not changing. So what they say, ki across the diametrically opposite ends, we can induce the EMF in this half part and we can induce the EMF in the other half part. While if you see in the loop, this gets positive, then this gets negative in the cyclic way. So overall flux changing through this circular loop is 0. So overall EMF is 0. But across the diametrically opposite points A and B, we have the EMF and which will be same. Because if we connect two batteries in parallel, the EMF will be same as just one of the batteries. So here also E equivalent will be BLV. So remember this part. If two wires, they are just connected parallel to each other and they both are moving, then the induced EMF will be same as just one of them, and we get the same answer. Next one, there is a rod AB, it slides on a V-shaped rail, V-shaped wire, this kind of thing. Okay? So as to connect the circuit, complete the circuit. They are saying कि it's moving with velocity v such that at any time OA is equals to OB is equals to L, and it is going to make equilateral triangle, because this is 60, so isosceles 60-degree triangle is equilateral, and magnetic field in the region is perpendicular and it is into the plane, and it has magnitude this. The induced EMF in the rod will be. Now see, they are saying कि induced EMF in the rod will be 0 or BLV or this. So how do we find it? How do we find it? And sometime the length is L. So if it is equilateral, so can you tell me what is the length of this wire? L only, because it's equilateral. So if the length of the wire is L, what will be the induced EMF? BLV. That's it. So I need not worry ki is it placed on a wire rail, is it inside a loop or what? If it's a wire is in motion, then across that wire, if the length is L, the magnetic field is B, velocity is V, induced EMF will be simply BLV or BVL. Need not worry about anything else. Okay? Straightforward. Now the motional EMF due to rotation of a rod. Rod is rotating, but the issue is कि at each and every point the velocity is not same, because in rotational motion or circular motion the omega is same for all the points, speed is not the same. At any random distance r, if I take a little element here of length dr, across this there will be some induced EMF. So if I say the little induced EMF across this will be B, the length is dr, and the speed will be across this point. If it's rotating with omega, r distance, so omega into r. Correct or not? This is the little EMF across this section. Now can you tell me what's the direction? If it's rotating in the anticlockwise sense, magnetic field is into the plane, so at each and every point velocity will be upwards. So V cross B gives me what? Inverse direction. That means this terminal will be higher potential, this terminal will be lower potential, and the induced EMF will be through the integration of this dE. So B can be taken out, omega is also out, or let's keep the omega outside, and it is r dr, which is r square by 2. You can take the limit from initial point to the final point. If it starts from the origin, the center of rotation, then we start from 0, ends at r, then we end at r. If it starts from r1, ends at r2, I can put r1 and r2 separately. So here, if r1 is 0 and r2 is the length of the rod, then the induced EMF will be b omega r square by 2, and which becomes L square by 2. Standard formula in the case of rotation. Okay. Let's take this question of induced EMF in the rotating rod. They are saying here conducting rod is there, AC rod is there, and total length is 4L. Okay. L is some unit of length. It's rotated about a point O, some point at some middle or inside this rod, not exactly at the end or not exactly at the midpoint, somewhere, such that ki AO distance is L and OC distance is 3L, like this. So it's rotated, great, it's rotated. Let's say it's rotated in the anti-clockwise sense. Now I know that ki just for this section OC, it's exactly the same as previous, and if I remove this section, then this section OA is exactly the same as the previous one. So if I say this OB section or OC section, this particular part, across this the EMF induced will be proportional to its length. So I can write that, because you know ki it's upwards, correct or not? So the higher potential will be O. lower will be C, and for this one it's going downwards, V cross B. So again the higher potential is O and the lower one is A. Tick. So what I'll write, VO minus VB, correct or not? The potential difference EMF, same thing. So VO minus VC, sorry, there is no B point, it's C. B is the field. Will be the formula which we wrote, B omega, length is 3L, so 3L square by 2. So 9B omega L square by 2. Okay. Same way I can do it for the OA section. Forget about the remaining rod. Okay, just look at the point of rotation. So VO minus VA will be B omega, length is L, L square by 2. They're asking the potential difference between VA, VO, VO and VC, and VC and VO. So we have got the answer. So VA minus VO is not B omega L square by 2, it is VO minus VA, because this is going to be the, okay? And VO minus VC is 9 omega or 9B omega L square by 2. And VA minus VC, alright, let's check about this, because both of them, by considering the direction as anti-clockwise, both of them are coming to be negative. They have just switched the terminals. So what I'll do, I'll look for this option C. So what I'll do, I'll subtract this result from this result. So here this is equation 1 and this is equation 2. Let's subtract equation 2 from equation 1. So here it will be VO minus VC, and I'll subtract it, VO minus VA. So what do we get? It is VA minus VC. VA minus VC we got, and it will be 9 B omega L square by 2 minus B omega L square by 2. So which is 8 B omega L square by 2. I hope by now you already got the answer. So 8 by 2 is 4 only. So VA minus VC is 4. Okay. So all, not all, but A, C and D, they all kind of look the similar, but the only thing is the sign here. Okay. So if it's rotating in anti-clockwise sense, then the rotation point is at the higher potential. Alright, let's check this problem. Rod of length 3L, exactly the same problem. I hope you guys can solve this. Break it into two parts. Take it. O, this C to D section is one rod, and this C to A section is another rod. And this time the rod is rotating in the clockwise sense. So this terminal will be positive, this negative, this will be positive, this negative, and we can write the potential difference. Okay. Next is the induced electric field in your electromagnetic induction. Why the electric field get induced? Just remember a single statement. Whenever in the region electric field changes, it produces magnetic field. Whenever in the region magnetic field changes, it produces electric field. Get the point? Alright. So when the magnetic field changes with time in the region, the electric field is induced, and this electric field, straightforward I am saying ki it is a non-conservative in nature. It is not electrostatic field, it is just induced electric field, non-conservative, and inside and outside the region like this. Check. Let's find out ki what is the electric field inside and outside. Achha, some points let's discuss. First of all, this field is different from electrostatic field, correct? This is a non-conservative field. The field lines are always forming closed loop, which never happened in the electrostatic. So induced electric field lines form closed loop. Okay, I'll write it here. Induced electric field lines form closed loop. Very important point. Closed loop. Okay. Okay. Force is equals to charge into electric field. It is valid. It will be valid for any charged particle in this field also. For one complete loop, the potential will not equal to 0. The potential difference will not be 0. There will be some work done. It's not 0. Okay. The line integral of E dot dl is not 0. The same thing. 0.5 and 0.6 are the same thing. Direction of induced field is same as the direction of induced current. The Lenz's law said the direction of induced EMF and the current is opposing the cause which produced. The same will happen for the electric field as well. Okay. So what they are saying ki this is a region of magnetic field, fixed, confined region, take a bound region. In this the magnetic field is changing with time. Changing with time. So certainly either they would give the function of magnetic field with time, or they will give you directly dB by dt, or some way through which I can calculate dB by dt. Okay. So inside, if I take any particular point at r distance, the induced electric field comes to be r by 2 times dB by dt, straightforward. And if I take any point which is outside, like the point 2, okay, so using the formula of induced EMF d phi by dt, and then the induced EMF is minus E dot dl formula, I can easily get the second result also, r square upon 2r dB by dt. So inside it's proportional to r, and outside it is inversely proportional to r. Just remember these two things. Alright. Moving on to the next part of this chapter, we have discussed quite a good amount of problems and important concepts of EMI, extensively of EMI. Let's proceed to the next part. Self-induction. What is self-induction? We know that there is coil, like solenoid is there, and if I pass current through the solenoid, magnetic field will pass, or magnetic field will be produced through the solenoid. Mu naught Ni, if you remember, correct or not? So what they say, ki if this magnetic field due to the current in the solenoid, it changes, then it again produces the induced field, and then it again will produce the induced electric current. So the current is already there in the coil, it's producing the field, the current is changing, the field is changing. This changing field again creates induced EMF and the induced current. That is called self-induction. Induction of EMF due to its own flux, due to its own magnetic field. So the induced EMF, we all know, will be minus d phi by dt. N is the number of loops and the phi is flux. Okay. So induced EMF is minus d phi by dt. Now, how to write the self-induction or the self-inductance? It's a property associated with loop, first of all. So what is self-inductance? We write it as L. Just inductance is also fine, or self-inductance. We define the self-inductance as phi through the loop by the current. So if I current is flowing through this loop, through this coil, and it produces phi flux, then the flux divided by I is the self-inductance. So in the same way, you guys study mutual inductance. So flux through one of the coils is basically due to the current in some another coil, then it will be the mutual inductance. Self-inductance. So suppose the self-inductance is given, current is given, can you find the flux associated? Yes, just cross multiply. So flux is Li. Again an important formula, remember this one, and we'll use it many a times. Okay. Okay. So let's proceed and let's look out for some important terms. Instantaneous EMF induced, we can easily write through this coil using d phi by dt. Now I know ki the phi is Li, correct? So the d phi by dt will be L di by dt, like this. So the induced EMF is minus di by dt, sorry, minus d phi by dt, so it is minus L di by dt. This is a very important formula. Induced EMF across an inductor The inductor whose inductance is L, given as L. Self-inductance, the unit is Henry or Weber per ampere. Self-inductance is positive value. It's just a value, just like resistance is usually positive. L depends upon the geometry of the loop, number of turns, the shape and size, the area, cross section, medium in which it is kept, because mu naught is there for the vacuum. For any other medium, mu r will be there. Now on what factors L does not depend? So it does not depend upon current. Okay? L does not change if the current changes. The flux will change. L does not change. Okay. What's an inductor? Inductor is nothing but a coil. Solenoid, a very little sharp small solenoid. Toroid also is fine. So solenoid wound in the shape of a circular loop is a toroid. Tick. Symbol of inductor or inductance is L. It's unit only. And in the circuit we draw it like a spring. Correct or not? The resistor is a zigzag little pattern. Inductor is a spring pattern. Okay, let's move forward. Now for the inductor, they say that we got the induced EMF. Now induced EMF is what? It's the potential difference. So they say ki current is passing through the inductor. Take the current is increasing, so di by dt is increasing. If di by dt is di by dt is positive. If di by dt is positive, potential difference A and B, VA minus VB, ठीक है, will be LDI by dt. ठीक है, तो initial will be higher, that's why the change in potential delta V will be minus LDI by dt. Change in potential has to be final minus initial, तो initial minus final is LDI by dt, तो final minus initial is minus LDI by dt. If the current is decreasing, then I know ki the final EMF will be higher. So VB and VA. So VB this time will be higher and it will be LDI by dt. Okay? Like this. And it's the symbol of the inductor, some little general points. Now if the inductor is connected in series, the series combination of inductor, I know ki in the resistor series combination, resistance is added. In the same way, for the inductors, inductance gets added in the series combination. Parallel combination, we use the inductance just like resistance. 1 upon L equivalent is 1 upon L1 plus 1 upon L2. Straightforward. Again, the parallel means the potential remains same. Next, let's take another question. Magnetic flux is given as 8 into 10 to the power minus 4 Weber, and it is linked with each turn of coil having 200 turns. When there is an electric current I equals 4 amperes in it, calculate the self-inductance. So I know that self-inductance is what? Phi by I. So phi divided by A will be 2 into 10 to the power minus 4. The unit is Henrys, like this. Straight question. Network shown is a part of a bigger electric circuit. The current 2 amperes is there and it's, let's suppose, going in this direction. Okay? And it is decreasing also at the rate of 2 amperes per second. Vp minus Vq equals, okay, so we are going to follow the potential tracing. Start from Vp. Across this battery the potential drops, so minus 2 volts. The current is there 2 amperes across this resistor. Again in the direction of current the potential drops, so again minus 2. And for this inductor, I know it is minus LDI by dt, so minus, the inductance is 1, LDI by dt itself is minus 2, so it is minus 2 and we reach Q. So take everything on the other side, so Vp minus Vq. Okay, this minus minus becomes plus, while this minus minus here only became plus, so on that side it is minus 2, so it remains 2 volts. So Vp minus Vq is 2 volts. So again a very crucial point ki the options are somewhat similar and somewhat, if we make a little mistake we can get the other option, which can just result in negative marking. Long solenoid has 1000 turns. When the current of 4 ampere flows through it, the magnetic flux linked with each turn of the solenoid is this. So total flux will be n times that individual flux. Correct or not? So total flux will be 1000 into 4 into 10 to the power minus 3, which is 4 Weber. Check. The self-inductance of the solenoid is, the current is there, so I know ki self-inductance is phi by I. So phi came out to be 4 and that is also 4. So 1 Henry, straightforward. See, such kind of questions NEET is asking. So definitely if you know the basics, if you know the proper way to solve, you can easily crack all of these questions. Next is, in an inductor of self-inductance 2 millihenry, the current changes with time according to the relation like this. Check. So in such kind of problems, you just need to write di by dt, that's it. They are saying at what time the EMF is 0. So I'll write this EMF as minus L di by dt. Okay, L is 2 millihenries, minus sign is fine, di by dt I'll integrate it. So differentiation of t square e to the power minus 2, apply the product rule and equate it to 0. So this 2 millihenry we can easily remove, not an issue. Differentiating this will get me 2t e to the power minus t plus t square e to the power minus t and minus 1 here, that is 0. So e to the power minus t can be easily cancelled. It's definitely non-zero here. So what do we get? T square minus 2t is 0. T is again non-zero. T is equals to 2 seconds. Easy problem or not? Not that easy, but again if you know the concepts properly, you can get the answer. Next topic of our today's session is alternating current. The last part, and again kind of an important part. Alternating current, you all know, is different from DC current. It has many different aspects. It has some benefits over the DC current, while there are some shortcomings as well. Everything has, correct. So what is alternating current? Alternating current is anything which continuously keeps on changing its direction. So one time it's going forward, and other moment it is going backward, another moment it is going forward, and keeps on doing the same thing, switching the directions continuously. This sine wave AC is one of the examples. Let's continue this forward. Okay. For the DC current we use batteries, DC source, and for the alternating current we use AC source. And the symbol of AC source is like this, correct or not? Thick. Okay. Now these are some examples of different types of alternating current waveforms. This is sinusoidal, this is square wave, this is triangle wave, this is sawtooth. So different waves. Just notice the direction is flipping, and that's what the AC current is all about. It's a periodic function and it should change the direction. Some important points ki why AC is better than DC. You should always go through these little theory points. Generation of AC is much cheaper as compared to DC. The EMI we just saw, electromagnetic induction, gives us AC current, alternating current. AC appliances are simple and do not require many repairs and maintenance. Great. The wide range of AC voltages is obtained by using transformer. Transformer is again a very important device which can just step up or step down the voltages, giving us flexibility to use and transport. The magnitude of current can be reduced by using an inductor or a capacitor without any appreciable energy loss. AC can easily be converted into DC using rectifier circuits, using capacitor and inductor combinations to become or to make it as a rectifier circuit. So AC can be converted to DC upon requirement. Transmission of AC over long distance is much efficient and requires, or it possesses, lesser energy losses. That's why one of the important points for mass generation of alternating current. But at the same time, there are some shortcomings as well. Peak value of AC is higher. So if somebody gets, let's say, God forbid, electrocuted through an AC source, she will receive a higher shock as compared to the same DC. ठीक? An AC is transmitted from the surface of conducting wires, hence it requires several strands of wire insulated from each other, because a wire is not just a solid core having a lots of free electrons. Definitely has. For the AC, the current only moves over the surface of the wire rather than through the whole of the cross section. Okay, fine. Let's move on to the main part, the mathematical part of the alternating current AC. Alternating current can be represented as per the sinusoidal waveform as I naught sine omega t plus phi, where the I naught is the peak value of the current, or we call it amplitude. Omega is the angular frequency of the AC supply or the AC source. T is the time period, F is the frequency, we all know. This phi is the initial phase or the phase constant. Tells us ki whatever we are discussing or whatever phase difference we are considering as compared to other components, so how to use it. Okay. Average value of the current in the half cycle is important, and it comes out to be, if you just put this I as sinusoidal waveform, then average value in the half cycle will be 2I naught by pi. Next is average value for the positive half is 2I naught by pi, and if I want to find the RMS value, the RMS value comes out to be I naught peak value divided by root 2, but this is only for sinusoidal. If it is not sinusoidal, then it will be something else. So just remember these points, important points. Okay. Lagging and leading concept. Suppose two waves are given, one of them is this one voltage and other one is this another voltage. So how to decide which one is lagging and which one is leading? You need to see it on the vertical axis, whether it's current or voltage, just see in the vertical axis. So vertical axis gives me lagging and leading knowledge. How do you see? You check which graph at t is equals to 0 is in the upward direction or relatively higher. I see this one. So this one becomes the extra phase or the leading. Extra something you are adding in the phase, so it is leading. So if this is V2, then this blue one is V2, and if this is V1, then this red one is V1. So always check the vertical axis, which one is lying higher. So the higher phase will lie higher on the vertical axis. That's how, leading and lagging. Okay. Moving on forward to the phasor. In the AC, everything is solved using phasors. If you understand the phasors, it becomes much easier. So phasor is what? I'll say, don't worry about this diagram anything. You just consider phasor as a vector. What is a vector? Vector has magnitude and angle. If you know the angle, instead of angle, now I will call it phase. Then you can do everything about the vector. So in the AC circuit, it's everything about vector addition. If I say vector here, it implies phasor. And it follows all the laws of vector addition. If I need to add voltages, I cannot do it algebraically. That V1 plus V2, all are AC voltages. I cannot do it. It will give me wrong answer. What do I do? Considering it as phasor, I'll do it like this. And this is just a notation. Don't think ki voltage has become a vector. It's a phasor. Okay? So phasor addition follows same laws, or I'll say ki it is phasor addition follows same laws as vector addition. What is phasor? Phasor is any quantity which is changing with time sinusoidally. So we have considered it as phasor. Okay. Let's check this example. They're asking about the phase difference between the current and the voltages. So the current here is represented as the sinusoidal, while the voltage is cosinusoidal, E. So first of all, and here some E naught, let's suppose. First of all, consider to convert the cos function to the sine function, or let's say the sine to the cos. Both should be the same type of trigonometric functions. Let's convert this to sine. I know that if I write pi by 2 minus whatever this angle, then it becomes sine theta. So what I'll do, instead of this, if I write sine pi by 2 minus this, will it give me cos theta? Correct. Rather than this, I can also do pi by 2 plus, because for sine, pi by 2 plus will be in second quadrant, gives me positive value. I need the positive cos. So this is also correct. And if this is correct, then E naught sine this pi by 2 and pi by 3 will get added, and it will be just cross multiply to 5 pi by 6. Now see, I have to compare current and voltage. It doesn't have anything added, it is just 0. It has 5 pi by 6. So what's the phase difference? 5 pi by 6, the last option. So what was the important point? If this is sine, this is cos, convert one of them to sine only. So both are in the sine, just convert it properly. And remember, omega t should be with a plus sign. So if you have done negative, then again do it correctly. Okay. What are different circuits we see in AC? So different circuits in AC are, if it is through a purely resistive load, only a resistor is there. If it is through a purely capacitive load, only capacitor is there. Or if it is through purely inductive load, only the inductor is there. Or if it's the combination, the inductor and the capacitor, inductor and the capacitor, capacitor and the resistor, resistor and the inductor, and all the three. LRC circuit or RLC circuit. Let's go through this part. Just a moment. All right. Now in these different types of circuits, what you need to understand is कि does the voltage lead or lag behind the current, or is it in the same phase? If you can decide that they are in the same phase or they lag or lead, then we can easily solve the problems based upon this. Okay. For this we need to define few more quantities. What is impedance? Impedance first of all has the unit of resistance, and impedance is kind of resistance or the opposition which is offered to the alternating current by this circuit, complete circuit, not just resistor, the complete circuit. Z is the impedance. And if we need to find the current, the net current, whether it is RMS value or it is peak value, we need to divide the net voltage by this thing and we get the RMS current. But remember that even though we are doing this, the current and the voltage may not be in the same phase. Even after getting this is only the value. So I'll write it here. This is only the value. Okay? So IRMS and VRMS may not be in the same phase. Important point. May not be in the same phase. Okay. Power in the AC circuits, we need to understand that how to find the power. The voltage is there, the current is there. This is V voltage. So the power is dissipated through the resistor. First of all, power cannot dissipate through a capacitor or an inductor. It is always dissipated through a resistor, and it comes out to be I RMS, the RMS value of current, into the resistance of the circuit. If it doesn't have resistance, there won't be any power dissipated. If you have VRMS, then it will be IRMS VRMS into cos phi, where what is this phi? This cos phi will be the power factor and phi is the phase difference between the current and the voltage. So the power factor cos phi is average power, which was that I RMS square R, and the RMS power is IRMS into VRMS, and cos phi comes out to be equal to R by Z. Okay, like this. Okay, so power in the AC circuits we have seen. Now different types of AC circuits. If it is a purely resistive circuit, then the current and voltage, they are in the same phase. If it is purely inductive, then here you see that the voltage and current are not in the same phase, and which one is lagging? The current is lagging, so the voltage leads here. So we write the voltage leads the current, while in the AC circuit you see its current having plus pi by 2, so the current leads. So what do we say? Voltage lags. So voltage lags in the capacitive, voltage leads in the inductive. So wherever the inductor is there, now see, we will see complex circuits. So wherever the inductor is there, whatever is current going through the inductor and whatever is the potential difference, the current through the inductor and the potential difference, so out of those, potential will always lead. Check, this is how we use it. Okay, the I naught will be V naught by R, the peak value. Here the I naught will be V naught by omega L. The omega L is the inductive reactance, the XL value of the circuit, while here it is V naught by 1 by omega C, technically speaking, and 1 by omega C is XC, the capacitive reactance. They kind of behave like what the resistance does, not exactly the same, but kind of that thing. Okay, so here they are saying the same thing. The voltage and the current, they are in the same phase. Here the current lags, the voltage leads, and here the current leads, the voltage lags. Check. Let's take a question from the AC. The equation of an alternating current is given as 220 sin omega t plus pi by 6. The equation of current is given as 10 sin omega t plus pi by 6. The impedance of the circuit is. For the impedance, I need not see about this omega t and everything else. To get the impedance, I just need to check the peak values. So the Z will be the peak value divided by the peak value of current. So 220 by 10, which is nothing but 22 ohms. And the unit of impedance or the reactance, everything comes out to be in ohms. Okay. So LR circuit is the combination of resistance and inductance. In this you need to check the inductive reactance, the reactance, and the net impedance of the circuit. So in this, if we draw the impedance triangle, and okay, here the impedance triangle and the voltage triangle. So on this axis I plot the resistance, on this axis I plot the inductive reactance, and the vector sum of these two gives me the net impedance. This is how. So in this triangle, if you see, this is the right angle triangle, so impedance will be R square plus XL square, where you know ki XL is omega L. In the same way, instead of R, I can write VR, which is I into R, and instead of VL, I can write it as I into XL, and instead of E, I can write it as I into Z. So if you remove I, we get this impedance diagram, impedance triangle. Get it? Like this. So using the phasor concept, you have to solve all the questions of your AC circuits. Let's take one more question. They are saying in the AC circuit, an alternating voltage E is equals to 200 root 2, so peak value is 200, and the RMS value of the voltage itself, peak value by root 2, which is 200 here. Okay. The omega is 100 here connected to the capacitor of capacity 1 microfarads. So XC here will be 1 by omega C. Omega is 100. This is omega. So 1 by 100 into capacitance is 1 microfarads 10 ki power minus 6. This becomes 10 ki power 4. That is XC and it's in ohms. The value of the RMS current. Okay. So RMS current is going to be Vrms upon XC. Vrms is 200 and XC is 10 to the power 4. So if we just take out 10 here, so it is 20 into 10 ki power minus 3 amperes. So 20 milliamperes, just matching the units. So be careful in this. Okay. Now, in the AC circuits, if you know that there is the condition of resonance where the external frequency omega matches with the natural frequency. The natural frequency is 1 upon under root LC. Using that condition, so resonance means the current peaks to the maximum value. Here what they are saying, ki inductor the voltage is 40, the capacitor the voltage is 10 and the resistor the voltage is 40. They are asking the amplitude of the current flowing through the LCR circuit is 10 root 2. The impedance of the circuit is. Okay. This is how they have given. Now see, I cannot write the net voltage as 40 plus 10 plus 40 because voltage is a phasor. It's a vector addition and it cannot be algebraic addition here. So if it's a vector addition, now see what we can do here. Just zoom it out. If it is a vector addition, now remember that this inductor and capacitor, so it will be VL minus VC on one side, so which is 30, and VR on the other side, which is 40. I draw the diagram, VR on this side, VL minus VC on this side. Net resistance or net voltage will be along the vector sum. So this is the right angle triangle, this is 40 volts, this is 30 volts. So I can guess that this resultant will be 50 volts, right angle triangle or not, 3, 4, 5. So they have given ki the RMS values of the, the amplitude of the current is 10 root 2. So the RMS value of current will be what? The amplitude divided by root 2, which is 10. And whenever the voltages are mentioned, they are always the RMS voltages. Potential difference across LCR, they are all RMS voltages. Okay? Without the equation are always RMS voltages. So RMS voltage of the circuit I got as 50. And for the impedance, you know what do? VRMS upon IRMS. So 50 upon 10, it is 5 ohms. Straightforward. This is how we solve the questions of alternating current AC circuit. And that's it for today. You guys revise all of the concepts of AC and EMI, the transformers, the LCR circuit, the self-inductance and the induced EMF, and you are done with the chapter. All right.